Good day, everyone. Welcome to day three of our Ansys online session. In today's class, we'll be talking about thermal analysis with our focus mainly on steady state thermal analysis. Okay, so by definition, thermal analysis helps engineers or engineers use thermal analysis to predict how their designs behave under various temperature conditions. Okay, so um, it's used to predict or determine how your model or your geometry will behave under various temperature conditions. Okay, but our focus for today's class is we have two types actually. We have two types of thermal analysis, namely steady state thermal. That is in ANSYS software. We have two types of thermal analysis: steady state thermal and transient state thermal analysis. Okay, these are the two major types of thermal analysis. And for steady state thermal, it analyzes the temperature distribution and heat transfer in a system or a body under constant thermal load. That means the thermal load does not change with time. That's why it's called steady state thermal analysis. Okay, the, 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 the the thermal load on acting on that body doesn't change with time, so it remains constant. While for transient, which is the opposite of steady state thermal, it examines how temperature changes over time in response to varying thermal load. So for transient determines how the temperature or the temperature conditions of your design or your system changes over time. Okay, with respect to the thermal load or the varying thermal load that was added on that body. So for this session, we will focus mainly on the steady state thermal analysis. Okay, so the first thing we'll do is to open up our ANSYS workbench. Okay, so our ANSYS workbench is now open. So we are going to conduct a steady state thermal analysis, on a heat sink. Okay, this is an example of a heat sink made up of aluminum alloy. So we are going to assign an aluminum alloy material type to this geometry and run a steady state thermal analysis. Okay, for the boundary conditions. Okay, at the bottom of this model, a heat source will be added. In this case, a temperature will be added. Okay, temperature of 800 degrees Celsius. Okay, temperature of 800 degrees Celsius will be added to the bottom part of this heat sink. Okay, that is to simulate a heat source from this bottom section. So the temperature of that heat source is 500. The temperature is 500 degrees Celsius. 500 degrees Celsius. Okay. Then for the while we are also going to add a should I say we are going to add a convention current to the body. Okay. We're going to add a convention current to the rest of the body. Convention current of room temperature, that is 20 degree Celsius, to the rest of this body, excluding this part, because this part has a heat source acting on it. Okay, so while the rest of the body we will use we'll apply a convention current to to simulate the heat temperature or air current over a body. In a convention is something that we experience in every part of our life. In this case, if you are in a room, let's say you are in a room or you're in any environment, the wind blowing over your body is called a convention current. Okay, so that natural breeze that is acting on this that has a cooling effect on this body, despite the heat source from here from the bottom, there is a cooling effect from the room, which has a natural or the standard room temperature of 20 to 25 degrees Celsius acting on this body. So it's kind of applying a cooling effect on this body. So we are going to add that conversion temperature of 20 to 25 degrees Celsius on every other surface of the body. Then we'll run our analysis and try to determine the thermal stress. Okay, our stress focus on our focus on this analysis is to determine how this heat source and convention current affects or causes a thermal stress on this particular heat sink body. Okay, so this is the thermal load 500 degrees Celsius, and this is the conversion load of 20 to 25 degrees Celsius. Okay, so these are the thermal load. And remember, from our definition, we are trying to analyze steady state thermal analysis analyzes temperature distribution and heat transfer in a system under constant thermal load. Okay, so this load will be constant, it doesn't change over time, and we use it to determine the temperature distribution. This is the stress value over this body, the thermal stress value over this body. So we are going to um, you can also determine the heat source to the heat flux rather. Heat flux, you can also determine the heat flux using this varying thermal load, not varying, it's constant thermal load, 500 degree or 800 or 500 to 800 degree heat source and 20 to 25-degree convection current. Okay, so the first thing you will do is to open up a steady state thermal analysis, add it to our project schematic. Okay, so I will drag and drop the steady state thermal to our project schematic. Okay, by default, remember I told you the engineering data, Ansys automatically adds a structural style for you whenever you open up a new analysis system, the project schematic. Ansys activates the structural style as a default material. So, but we want to use in this our analysis, we want to use the aluminum alloy. So you are going to go to our engineering data and add the aluminum alloy to our material library. So, and how do you do that? The next thing you do is to right click on your engineering data, then click on edit. Then under this edit, we have two tabs here. We have two tabs at the top, just below the standard toolbar. You have the filter engineering data and the engineering data sources. So I'm going to switch, currently it's at filter engineering data. So I'm going to switch to engineering data sources by left clicking on it. Okay, I will select under the engineering data sources, which is here. This is engineering data sources. I will select general materials. Okay, I want to select general materials. Just left click on it once, it will open up here. So you can see the next tab, the next section is outline of general materials. So I want to select a general material. Okay, so I will scroll down through this material, select this one, and just here at the top of the next section, you see the name of the material. Okay, so in your own Ansys, the name might be displayed here, but in mine it wasn't displayed. I'm just having general materials here, so there's an issue with mine. But in your own Ansys, you can see the name. While you scroll through this outline of general material, you see the different names of this material. But if you can't find it here, whenever you click on any of this general material, the names will be displayed here under the properties of outline row. Then you can see column, then you have air. The first material I selected was air, so I'll click on the second one. Okay, and it will see you see it will change. It has changed now to aluminum alloy. So I'm telling you that this particular material that I selected is aluminum alloy. So just beside the material, under the add column, you can see this plus sign. You will click on this plus sign to add it to our material library. So when I click on the plus sign, a book will display beside it, telling you that you have added it to the library for this your analysis. So you can now go back and under your standard toolbar, you see the engineering data. Because it's open, you can click on this X to cancel it. You have added it to your material library. So the next thing we will do is to add our geometry, to insert our geometry. So I will right click on geometry, then scroll down to import geometry, go to the browse, now insert a heatsink geometry from our file explorer. So I will select the heatsink and click open. So our geometry has been added. You can see the check mark button. Now the next thing we'll do is to double click on model to open up our Ansys Mechanical. Okay, so where we can continue with the meshing and adding of boundary condition. So I'll switch over to the Ansys Mechanical. Our heatsink is already opened in our Ansys Mechanical. Okay, so the next step we'll do from the project schematic, you can see geometry has been added. But if you click on the geometry, okay, and you scroll down to under the details of geometry, okay, no, this is geometry import, sorry. Under geometry, not geometry import, but geometry rather, you can see our heatsink there. Okay, so when I click on it, details of heatsink, which is our geometry, scroll down to the material tab. Under materials, the material assignment is structural steel. It's still currently as structural steel, but remember we've added aluminum alloy to the library, so we want to change it. We want to select aluminum alloy to this. We want to assign aluminum alloy material to this our heatsink. Okay, so you cannot assign it if you did not select, if you did not add that aluminum in your material library. So that's why it's important to always add it to your library so that you can come here and change it anytime you want. Okay, so next thing we'll do is to make sure that our aluminum alloy is being assigned to this heatsink geometry. So you go under materials assignment, then click on this. Okay, you see this box here, this arrow box here, click on it to open up your library. So we have the aluminum alloy, we have the structural steel. You also have the history of just above it, you have the history of materials you've used earlier in your previous analysis. But in this case, we want aluminum alloy, so I'll click on aluminum alloy to assign it. Now you can see that our material has changed to aluminum alloy. Okay, so if I should click on that heatsink again, let's click on it to open up the details. If I should scroll down to the material, you can see that we have aluminum alloy as the material of this heatsink geometry. So the next thing we'll do is to generate a mesh for this. Okay, so we are going to generate a random mesh. We won't pay much attention to the mesh refinement of this particular model. So any mesh that is generated will work with that. Okay, so I will click on the mesh and change the element size. Right, I will say 20 millimeter. Let's start with that 20 millimeter and try to view it. Because 20 millimeter is too big. Okay, how this 20 millimeter is being displayed here by this circle that hovers around the cursor. Okay, you can see it's trying to tell you the size of 20 millimeter relative to your canvas. Okay, you can see it's very, very big. Okay, which is too small, so I'll change it to 5 millimeter. So I'll create 5 and enter. Okay, this is a little bit better, but it's still too big. So let's say we can work with this actually. So I will say generate mesh. I'll right click on mesh and say generate mesh. We'll wait for our mesh to generate. Currently it's at 5%. Okay, now we have okay, we have our mesh ready. So this is okay. So remember I said we will not pay much attention into the mesh refinement, but even by mesh refinement standards, this is also a good mesh. Right. So the next thing we'll do is to assign our boundary conditions. So how do you assign boundary condition? You go to your steady state thema, as you can see in the project schematic, then right click on it and insert. Okay, the first thing we are going to insert is the temperature. That is that heat source I mentioned earlier that will be at the bottom of the heatsink. So click on temperature to activate it. Then I'll assign it to the particular geometry I want it to be. So I want the heat source, which is this temperature, to be applied at this bottom. Then I will select I'll use the fixed selector to select this button. Then I'll click apply. Okay, so for the temperature currently it's at 22 degrees Celsius, but I want to change it. You will change it to 800 degrees Celsius. Okay, between 500 to 800. So in this case we'll select 650 degrees Celsius. Press enter, and our temperature has been assigned. I can see the check mark telling you that all parameters is complete. So the next thing we are going to add is a convention current. Okay, so I will right click on the steady state thema and insert convention. Okay, that is the airflow in the room around that is touching this body. Okay, airflow in that room, particular room, warehouse, or wherever this material is that is hitting it, and you are going to use normal room temperature. Okay, you are acting on this body, kind of, and acting is kind of giving it a cooling effect. So we are going to apply that. So we have to apply to every other surfaces of this model because the airflow is touching every surface of this except the bottom. Okay, so how do we do that? You are going to use the fixed selector and click and drag. I can select it one after the other by click, then hold down your control and start selecting all surfaces. but you can also do that by holding down your left click button on your mouse and then drag it all through the surface you want to select. Okay, that will be faster. Okay, we need to make sure we turned it properly and hold down this time around. I'll hold down Control and select the remaining part. Okay, so if you're not careful, you go ahead and click on a part, you might end up deselecting everything you have done. Okay, okay, hold down Control and select the other part. Okay, then I'll click Apply. 29. Okay, our convention has been added to every surface. Okay, except this bottom surface where the heat source is being directed on. Okay, so that's good. Then the next thing we have to add is the firm coefficient. So in this case, we're going to add 10 watts per millimeter. Okay. Then for the ambient temperature, it's set at 22 degrees Celsius. But you can, if you are not sure if you are not sure about the ambient temperature, which is 22 degrees Celsius, you can insert it from your, um, you can import it from your Ansys library. Okay. 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 Currently, my library is not available. Okay, my library is not available, but you have the option to import it from your Ansys library where you have the stagnant air, the humidified air, and those like so. But in this case, we want to use the stagnant air, so um, we are going to impute the room temperature, which is I said 20 to 25 degrees Celsius. So we use the center value like 22 degrees Celsius. So we are going to click on enter. So now we've added our conversion. You can see the blue check mark button. Okay. So the next thing we'll go to your solutions tab. That is solutions tab. You right click to add your result, the result you want to generate. So you want to generate the thermal. Want to know the how these parameters, these temperature loads act on this body. Okay, so we are going to determine the first thing we are going to determine is the temperature distribution on this body, and the second thing we are going to determine is the total heat flux on this body. Okay, so you right click on solution and say solve. Then wait for it to solve. So we are trying to determine the temperature distribution on this body and the total heat flux on this body as a result of the temperature loads that we added to it. Okay, so that's the aim of this analysis, this steady state analysis. The value is remain constant; it doesn't change with time. So our result is almost ready. So I will click on the temperature. I'm going to click on the temperature. Okay. Our result is ready. So when I click on the temperature, you can see the temperature distribution on this body. Okay. So you can click on the animation to view how the temperature is being distributed on this part of the body. Right. So you can also view the total heat flux. So for the total heat flux, we have a maximum of 101.9 watts per millimeter square. That's the maximum heat flux. And you can also use the animation to view how the total heat flux is being distributed on our heat sink. Okay, so this an analysis, yeah, the temperature is actually quite small. That's why it doesn't really affect you. As you can see, this blue side, this the top part that has a blue contour, telling you that there's very low. This side has very low temperature distribution, like 11 degrees Celsius. Okay, so you can telling you that's to tell you that the temperature, the heat source is actually very low and it doesn't really affect this top part of the body that much. But you can also increase that too. Right, so I will stop this and go back and change it. I will adjust the temperature value from 650 to 2000 degrees Celsius. Press enter, then you generate the mesh. Okay, the mesh is generated. You can, if it doesn't, you can generate the mesh. Okay, but in this case the mesh is still okay. So next thing we'll do is to resolve our analysis. Okay, now we have a different result. Okay, okay, although it's kind of similar to the previous one. Okay, so yeah, in the heat flux now we have a heat flux now of 322 watts per millimeter square, a maximum heat flux of 322 max per millimeter square. Okay, you can see and view that now. Okay, so that's how you carry out a steady state thermal analysis. Okay, so this is a thermal analysis for you. The value doesn't change in time, it's constant, as opposed to the transient thermal analysis. So for the transient thermal analysis, at every instant in time, you have a different result. At every instant in time, you have a different result. But for steady state thermal analysis, the result is constant. So when you look at the graph or the plot, you have a very straight line. The result does not change. Okay? So that should conclude this our session. So in our advanced classes, we are going to go dive deep into this steady state thermal analysis and transient state thermal analysis. So we'll go deep into them, try carry out more advanced analysis on this thermal, and we are going to carry out more advanced thermal analysis in our advanced classes. So then with that, so that should conclude our session. So thank you very much. We'll meet in our next class.